somewhere beyond the edge of the solar system, more than 12 billion miles from Earth, a spacecraft launched during the Carter administration is still alive. Think about what that means for a moment. Voyager 2 left Earth in 1977. The technology inside it was designed and built in the early 1970s. The engineers who drew up its blueprints were working before personal computers existed, before the internet, before most of the tools we now take for granted in any engineering lab. And yet that spacecraft is still out there, still functioning, still sending data back, still alive in a place where temperatures drop to within a few degrees of absolute zero, the coldest anything can physically get. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. That's the paradox at the center of this story. Voyager 2 is operating in one of the most hostile environments in the known universe. It's not orbiting a warm planet. It's not basking in sunlight. It crossed into interstellar space on November 5, 2018, at a distance of 119.7 astronomical units from the Sun. That's roughly 11 billion miles. It has kept moving since then. More than 12 billion miles now. No spacecraft in history, except its twin Voyager 1, has ever gone that far. Interstellar space, the region between the stars. A place so remote that the sun itself appears as nothing more than a bright point of light, indistinguishable from millions of others. A place where the solar wind, the constant stream of charged particles flowing outward from our star, has finally run out of energy and stopped. A place where the sun's magnetic field no longer dominates, where the warmth and influence of our star fade into something else entirely. And Voyager 2 is not just passing through, it's operating, it's measuring, it's transmitting. Every single day, it sends back data about what interstellar space actually looks and feels like from the inside. No observatory on Earth can do that. No telescope in orbit can do that. Only Voyager 2. So how does it survive? The cold alone should have stopped it decades ago. Spacecraft depend on electronics, fuel lines, mechanical systems. These things have temperature limits. Too cold and fuel freezes. Too cold and materials become brittle. Too cold and the whole machine stops being a machine and starts being wreckage. At 12 billion miles from the sun, sunlight delivers almost nothing. Solar panels would be useless. The sun is so far away that its light at that distance carries a tiny fraction of the energy it delivers here on Earth, roughly 1 divided by 1,700 of what we receive. You could cover Voyager 2 in the most efficient solar panels ever built, and they would still be useless out there. Whatever is keeping this spacecraft alive, it isn't sunlight. The answer involves 3 separate things, all of them working together. It involves engineering choices made 50 years ago that turned out to be exactly right. It involves some genuinely counterintuitive physics about how heat moves or fails to move in environments that are nearly empty. And it involves some surprising properties of interstellar space itself that scientists didn't fully understand until Voyager 2 went there and started measuring. Some of what Voyager 2 found out there was completely unexpected. The environment beyond the heliosphere is not what most models predicted. The numbers coming back from its instruments surprised the researchers analyzing them. And some of those surprises actually help explain how the spacecraft survives, even if they seem at first to make the question harder to answer rather than easier. We'll get to all of it. The plutonium at the heart of the spacecraft, the fuel lines that absolutely cannot freeze, the strange thermal properties of a near vacuum, the boundary Voyager 2 crossed in 2018, and what its instruments recorded as it crossed, and the physics reason why something that sounds like it should be the coldest environment imaginable is, in a very specific technical sense, not quite what it appears to be. And to understand why, you have to understand what interstellar space actually is, because it turns out to be far stranger than most people imagine. For most of human history, people imagined space as a simple void, dark, empty, cold, no air, no sound, nothing. And for the space between planets, that picture is mostly right. But the space between stars is something else entirely. It's not empty, it's not simple. And in some ways, it's not even cold in the way most people mean when they use that word. Understanding what Voyager 2 actually crossed in 2018 requires understanding what our sun does to the space around it, and what that space looks like once you get far enough away that the sun can no longer reach you. Our sun is constantly exhaling. Every second, it streams charged particles outward in all directions at speeds of roughly 1,000,000 miles per hour. This is the solar wind. It isn't metaphorical. It's a real physical flow of plasma, mostly electrons and protons, blasting outward past Mercury, past Venus, past Earth, past all the planets, past even the distant orbits of Uranus and Neptune. The solar wind carries with it the sun's magnetic field, stretched and draped across enormous distances. Together, the solar wind and that magnetic field inflate a vast bubble around our solar system. Astronomers call it the heliosphere. Think of it as the sun's atmosphere, not the glowing outer layers you can see in photographs, but an invisible atmospheric bubble extending tens of billions of miles in every direction. The heliosphere is enormous. It dwarfs everything inside it. All 8 planets, every moon, every asteroid, every comet in our solar system fits comfortably within this bubble with room to spare. The outer planets feel like they're far away from us, and they are, by human scales. But from the perspective of the heliosphere, Neptune is practically in the sun's backyard. The bubble extends roughly 100 astronomical units from the sun in most directions. 1 astronomical unit is the distance from Earth to the sun, about 93 million miles. So we're talking about a bubble that stretches nearly 10 billion miles from the sun before it starts to run out of steam. And that's exactly what happens. The solar wind doesn't stop abruptly, it slows. At a region called the termination shock, roughly 75 to 90 AU from the sun, the solar wind decelerates dramatically. It hits a kind of traffic jam where the pressure from interstellar space begins to push back. The plasma bunches up and slows from supersonic to subsonic speeds. Beyond that point, in the region called the heliosheath, the solar wind is still present, but sluggish and turbulent. It's been compressed and heated and rerouted. The sun's influence is weakening. Eventually, at the heliopause, it gives out entirely. The heliopause is the true boundary, the line where solar wind pressure and interstellar pressure balance each other out. Cross that line, and you're no longer inside the sun's bubble. You're in interstellar space. On November 5th, 2018, Voyager 2 crossed that line. It was 119.7 astronomical units from the sun. That's roughly 11.1 billion miles. Moving at about 34,000 miles per hour relative to the sun, it had taken the spacecraft 41 years to get there. The crossing itself happened fast, less than 1 day. The instruments aboard recorded the shift clearly. The solar wind particles dropped off. The interstellar plasma appeared. The magnetic field changed character. One environment gave way to another in a matter of hours. It was, by any measure, one of the most significant crossings in the history of space exploration. humanity had placed an instrument at the boundary between our solar system and the rest of the galaxy, and it had measured what that boundary actually looks like up close. Yet what typically escapes most people's notice is this. The space Voyager 2 entered on that day isn't empty. It isn't a featureless void. The interstellar medium is filled with gas and dust and magnetic fields and charged particles. It has structure, it has density, it has a temperature. And that temperature is the part that surprises almost everyone who hears it. The plasma in the very local interstellar medium, the region just beyond the heliopause that Voyager 2 now moves through, registers at somewhere between 30,000 and 50,000 Kelvin. That's hotter than scientists predicted. In fact, it's hotter than the surfaces of many stars. The surface of our sun is about 5,500 degrees Celsius. The plasma outside our solar system runs far hotter than that. On paper, think about what that means for a second. We have a spacecraft operating in a region of space where the measured temperature exceeds that of stellar surfaces. And yet, Voyager 2 isn't being incinerated. It isn't heating up. It's functioning in what engineers describe as an extraordinarily cold environment. How do those two things fit together? The answer requires separating two concepts that our everyday experience tends to blur together. Temperature and heat are not the same thing. Temperature measures the average kinetic energy of individual particles. Heat is the total thermal energy available to transfer to something else. And that distinction matters enormously out there, because the interstellar medium is extraordinarily thin. The particle density is almost nothing. There are perhaps a handful of atoms per cubic centimeter. Compare that to the air you're breathing right now, which contains roughly 27 billion atoms per cubic centimeter. The particles in interstellar space are energetic. There are just almost none of them, so they carry almost no transferable heat. Voyager 2 passes through this plasma the way a person walks through a fog so thin it barely registers. The individual droplets might be there, but there aren't enough of them to get you wet. Beyond the heliopause, the spacecraft is essentially thermally isolated from its surroundings. The environment isn't transferring meaningful heat to the spacecraft in either direction. The real thermal challenge for Voyager 2 has nothing to do with the temperature of the interstellar medium and everything to do with what the spacecraft generates internally and what it loses to the radiative cold of space. That story gets complicated quickly, but before we get there, it's worth sitting with what Voyager 2 actually measured as it crossed into this strange territory. What it found there forced scientists to rethink what they thought they knew about the space between the stars. On November 5, 2018, Voyager 2's plasma science instrument recorded something it had never recorded before. The solar wind stopped. Not gradually, not slowly over weeks or months. In less than a single day, the stream of charged particles flowing outward from the sun simply ceased. The plasma surrounding the spacecraft changed entirely. The density shifted. The composition shifted. Everything the instrument had been measuring for 4 decades changed at once, in a matter of hours. Scientists watching the data come in knew immediately what they were seeing. Voyager 2 had crossed the heliopause. It had left the sun's domain and entered the space between the stars. The moment itself was almost shockingly abrupt. After 41 years of travel, the crossing took less time than a single workday. Here's what made this crossing different from anything scientists had seen before. Voyager 1 had crossed the heliopause in 2012, about 6 years earlier. That crossing was historic, but Voyager 1's plasma science instrument had stopped functioning years before it reached the boundary. Scientists could measure certain things. They could track energetic particles. They could monitor magnetic fields. What they couldn't do was directly measure the plasma itself, the density, the temperature, the flow speed of the material on both sides of the boundary. They had to infer, they had to estimate. The picture was incomplete. Voyager 2 still had a working plasma science instrument. That changed everything. For the first time in history, scientists had a functioning plasma detector at the Heliopause. They could measure the boundary directly, not infer it, not model it, measure it. The significance of this direct measurement cannot be overstated. For decades, the Heliopause had been a boundary scientists theorized about, but had never directly observed with active instrumentation. Previous observations relied on indirect methods, inferring the boundary's location from particle behavior and magnetic field changes alone. With Voyager 2's working plasma instrument, scientists could finally see the boundary itself. They could measure the exact density gradient, the temperature jump, and the velocity shift in real time. This transformed the Heliopause from a hypothetical construct into a confirmed, measurable physical phenomenon. The data provided unprecedented precision about the location and nature of the solar system's outer edge. For the first time, scientists held direct measurements from both sides of the Heliopause. The data that came back was remarkable. On the solar wind side, the plasma was fast and relatively sparse. It was streaming outward from the sun at hundreds of kilometers per second. On the interstellar side, the plasma was slower, denser, and moving in a completely different direction. Think about what that means. Two completely distinct regions of space, separated by a boundary thin enough to cross in hours, each filled with plasma that behaves entirely differently. The solar wind, which had been pushing outward for the entirety of Voyager 2's journey, simply ended, and the interstellar medium, which had existed around our solar system long before the sun was born, began. But the transition wasn't perfectly clean. In the region just before the Heliopause, roughly 1.5 astronomical units wide, something interesting happened. The plasma slowed down, it heated up. The density approximately doubled compared to typical solar wind plasma further inward. This boundary layer is where the solar wind, having traveled billions of miles from the sun, finally runs out of momentum. It piles up, it compresses, it loses its outward velocity and grows denser and hotter as it pushes against the interstellar medium, pressing in from the other side. Voyager 2 passed through this region before it crossed the Heliopause itself. The instruments were recording the whole time. The particle data told its own story. Inside the heliosphere, energetic particles from the sun dominate. Cosmic rays from outside the solar system are partially blocked by the heliosphere's bubble. As Voyager 2 approached and then crossed the Heliopause, those proportions flipped. Solar particles dropped sharply. Cosmic rays surged. Within days of the crossing, the cosmic ray count had increased dramatically. The spacecraft wasn't just crossing a line on a map. It was crossing a real physical boundary with measurable consequences for the environment around it. The instruments confirmed it from multiple directions simultaneously: plasma density, particle composition, magnetic field orientation. They all changed at once. Now compare this to Voyager 1. Both spacecraft crossed the Heliopause. Both saw cosmic ray counts rise as solar particle counts fell. The magnetic field behavior was broadly similar, but Voyager 1's crossing happened at a different location, on a different trajectory, in a different direction relative to the sun's motion through the galaxy. The Heliopause isn't a perfect sphere. The sun moves through the galaxy, and that motion shapes the heliosphere asymmetrically, like a comet with a longer tail behind it and a compressed nose in front. Voyager 1 crossed in one direction. Voyager 2 crossed in another. The two datasets together gave scientists something they'd never had: two data points on the actual shape of the heliosphere. Two measurements from two different locations on a boundary that no probe had ever directly sampled before. But here's what most people don't realize. Even after crossing the Heliopause, Voyager 2 didn't enter clean, undisturbed interstellar space. Scientists examining the data found that the region just beyond the boundary was still perturbed, still showing signs of influence from the heliosphere behind it. Solar particles were still trickling through, not in large numbers. A faint leak, like light coming through a crack under a door. If the heliosphere is a bubble, it turns out the walls aren't perfectly sealed. Material from inside is escaping into interstellar space in small quantities. Voyager 2 detected this. The instruments confirmed it. The spacecraft was beyond the heliopause, technically in interstellar space, and yet it wasn't entirely free of the sun's reach. This finding surprised researchers. Models of the heliosphere had generally treated the heliopause as a relatively firm boundary. The new data suggested something more complicated. The transition from heliosphere to interstellar medium isn't a sharp wall, it's a zone, a region where the two environments interact, where particles from one side slip into the other, where the boundary itself breathes slightly with the changing pressure of the solar wind. Voyager 2 is somewhere in that transitional zone right now, not in the clean interstellar medium that lies beyond it, still in the perturbed region just outside the heliosphere's edge. How wide that zone extends and how long Voyager 2 will take to cross it entirely remains an open question. What the November 2018 crossing gave science was irreplaceable. A direct measurement of the heliopause with working instruments from both sides. A comparison between the plasma inside the heliosphere and the plasma beyond it. A confirmation that the boundary is real and physically distinct, not just a theoretical construct. And a set of surprises: the leakage, the asymmetry, the perturbed transitional zone that no model had fully anticipated. Voyager 1 had crossed first, but without its plasma instrument, it couldn't tell the full story. Voyager 2 filled in what was missing. The boundary was real, it was measurable, and Voyager 2 had crossed it, though what lay just beyond it was not quite what anyone had expected. Here is the part that takes a moment to wrap your head around. The plasma in interstellar space near Voyager 2 is not cold. Scientists expected it to be cold. Models predicted temperatures somewhere between 15,000 and 30,000 Kelvin in the very local interstellar medium. What Voyager 2 actually measured was 30,000 to 50,000 Kelvin. Hotter than predicted. Hotter, in fact, than the surface of many stars. Our own sun's surface sits at around 5,800 Kelvin. The plasma surrounding Voyager 2 out in interstellar space is running somewhere between 5 and 8 times hotter than that. So the natural question is obvious. If the environment around Voyager 2 is that hot, why isn't the spacecraft being cooked? Why hasn't it heated up? Why do we keep talking about the cold of interstellar space when the numbers say something completely different? The answer comes down to a distinction that most people never have to think about. Temperature and heat are not the same thing. They feel like the same thing in everyday life. Touch something hot and you feel heat. Stand near a fire and warmth radiates toward you. The two concepts seem inseparable, but they're not. Temperature is a measure of the average kinetic energy of individual particles. It tells you how fast those particles are moving. Heat, on the other hand, is the total thermal energy that can actually be transferred from one object to another. And to transfer heat, you need particles making contact. You need collisions. You need something to carry the energy from one place to another. In interstellar space, there is almost nothing to do that. Think about what the interstellar medium actually looks like on a physical level. Between the stars, on average, there is roughly 1 particle per cubic centimeter of space. 1. A cubic centimeter is about the size of a sugar cube. In the air around you right now, that same sugar cube volume contains something in the range of 27 quintillion molecules. The difference is not just large, it cannot readily be described through ordinary comparison or standard measurement. The interstellar medium is not a gas in any sense that we'd recognize. It is closer to a vacuum than to anything we interact with in daily life. And within that vacuum, there are individual particles carrying enormous amounts of kinetic energy, fast-moving, energetic, but almost entirely alone. This is where the analogy helps. Imagine a large, dark room. The room is filled with a tiny number of extremely fast-moving metal balls, each one ricocheting around at incredible speed. If you stood in that room, you would almost certainly never get hit. The balls are moving fast enough to shatter bone, but there are so few of them that the odds of a single collision are vanishingly small. You could stand there for a very long time and feel almost nothing. Now fill that same room with air at normal temperature. Suddenly, trillions of molecules are hitting your skin every second, each one carrying only a small amount of energy. The individual energy per particle is nothing compared to those metal balls. But because there are so many more collisions, you feel warmth. The air heats you. The room heats you. The metal balls, despite their ferocious speed, mostly don't. Interstellar space is the room with the metal balls. Individual particles carry extraordinary amounts of kinetic energy. The temperature is real, the measurement is real, but the collisions almost never happen. Voyager 2 is moving through that environment, and the plasma around it simply has no effective way to transfer its energy to the spacecraft. The particles are too sparse, too far apart, too rarely in contact with anything at all. Heat transfer works through three mechanisms. Conduction requires direct contact between molecules. Convection requires a fluid or gas dense enough to circulate and carry thermal energy. Radiation involves the emission and absorption of electromagnetic energy, which does occur in space, but from sources like the Sun, and at Voyager 2's current distance, even solar radiation has faded to essentially nothing. None of these mechanisms function the way they do on Earth when you're surrounded by vacuum. Conduction requires contact. There is no contact. Convection requires density. There is no density. Radiation from the interstellar plasma is present, but so faint, so spread out across such an enormous volume that it contributes almost nothing to the spacecraft's thermal environment. The environment cannot heat Voyager 2 because the environment has almost no way to reach it. This principle matters enormously for spacecraft design. Engineers cannot rely on the surrounding environment to dissipate heat through ordinary mechanisms. Instead, they must design spacecraft that radiate their excess thermal energy directly into space, shedding warmth through infrared radiation into the void. For Voyager 2, this means the spacecraft depends entirely on its own radiative cooling systems to maintain safe operating temperatures. The extreme isolation that makes the environment unable to heat the spacecraft also means the spacecraft must manage its own thermal budget with complete independence from external conditions. This is also why the cold of deep space is somewhat misleading as a concept. Yes, if you placed a thermometer in interstellar space and waited long enough, it would eventually equilibrate with its surroundings and register temperatures near absolute zero. But that process would take an extraordinarily long time. The thermometer would be radiating its own heat into space, slowly losing thermal energy, and the surrounding medium would be contributing almost nothing back. The spacecraft does the same thing. It radiates heat outward into the void. The void gives almost nothing back, which means that, from Voyager 2's perspective, the real danger was never getting cooked by hot plasma. The real danger has always been losing its own heat faster than it can generate new heat. Voyager 2's data confirmed something else that scientists found surprising. The interstellar plasma is not only hotter than expected, it's also denser than the plasma inside the heliosphere. Heliospheric plasma is hot but sparse. Interstellar plasma, just beyond the heliopause, is somewhat cooler but packed together a little more tightly. Not dense in any earthly sense, still extraordinarily thin by any human standard, but denser in comparison to what sits inside the solar wind bubble. This reversal of density and temperature between the two regions was one of the more unexpected findings from Voyager 2's crossing. It tells scientists something about how the heliosphere and the interstellar medium interact, about the pressures on either side of that boundary, about the way the sun's influence shapes the space around it. The numbers coming back from the plasma science instrument forced researchers to revisit models they had trusted for decades. These findings suggest that the boundary between the sun's domain and the broader galaxy is far more complex than previously understood. The interaction involves intricate pressure balances, magnetic field dynamics, and particle physics that extend well beyond simple solar wind expansion. Understanding this border region helps scientists grasp how stars influence their local galactic neighborhoods and how that influence eventually fades into the greater interstellar environment. So when people picture Voyager 2 out in interstellar space, suffering through unimaginable cold, the picture is both right and wrong. The emptiness is real. The isolation is real. The temperatures that a properly calibrated instrument would eventually register near that spacecraft are brutally low, but the mechanism by which that cold reaches the spacecraft is almost entirely absent. There are simply not enough particles out there to make the transfer happen efficiently. Voyager 2 is thermally cut off from its environment in a way that nothing on Earth ever is. Not because the environment is gentle, but because the environment is barely there. The spacecraft isn't surviving despite the cold. It's surviving because the environment around it is so empty that the cold can barely reach it at all. The real answer to why Voyager 2 hasn't frozen has been aboard the spacecraft since the day it launched. It has nothing to do with the temperature of interstellar plasma. It has nothing to do with the sun's distant warmth reaching across 12 billion miles. The answer is 3 metal cylinders mounted on a boom extending away from the spacecraft's main body. 3 generators, each one packed with a radioactive material that has been quietly releasing heat since 1977. No switches to flip, no fuel lines to maintain, no solar panels to angle toward a light source. Just steady, continuous, unstoppable decay. That is what has kept Voyager 2 alive in the coldest, emptiest place any human-made object has ever traveled. Those generators are called radioisotope thermoelectric generators, RTGs. Each one contains 24 pressed spheres of plutonium-238 oxide. Not weapons-grade plutonium, not the kind used in nuclear reactors or warheads. Plutonium-238 is a specific isotope selected for one reason above all others. It decays slowly, predictably, and when it decays, it releases heat, steady, consistent heat that doesn't require any reaction to be triggered, any combustion to be sustained, any external source of energy to keep going. The plutonium simply exists, and in existing, it generates warmth. That process has been running continuously since Voyager 2 lifted off from Cape Canaveral on August 20th, 1977. To understand why this works, you need to understand what radioactive decay actually is. Inside an atom, the nucleus is made of protons and neutrons. In some atoms, that nucleus is unstable. The nucleons, the protons and neutrons packed together in the core, want to rearrange themselves into a lower energy configuration. When they do, they release energy. In the case of plutonium-238, that released energy comes out primarily as heat. No explosion, no chain reaction, just a gradual, continuous release of thermal energy as atom after atom after atom settles into a more stable state. Think about what that means for a spacecraft. You have a power source that requires no oxygen, no combustion, no moving parts. It cannot run out of fuel in any sudden way. It cannot be switched off by a malfunction. It simply decays, and in decaying, it provides heat. Each of Voyager 2's 3 RTGs weighed about 37.7 kilograms. That includes roughly 4.5 kilograms of plutonium-238 per generator. Together, at the moment of launch, the 3 RTGs provided the spacecraft with approximately 470 watts of electrical power. 470 watts. That's less than 5 standard incandescent light bulbs. To put that in perspective, the laptop or phone you're using right now likely draws more power than that, and yet 470 watts was enough to run every instrument on Voyager 2, power its transmitter, operate its computers, and control its attitude thrusters across a journey of 12 billion miles. The efficiency of the design is extraordinary when you consider what it accomplished with that limited power budget. But the RTG doesn't just produce electricity. That's the part that's easy to miss. Before the electrical power is generated, there is heat. Raw thermal energy coming off the decaying plutonium. Some of that heat gets converted into electricity through the thermocouple system, but not all of it. A significant portion of that heat becomes waste heat, radiating through the spacecraft's structure, and that waste heat is just as critical to Voyager 2's survival as the electricity it produces. We'll come back to that. First, it's worth understanding how the electricity gets made at all. The conversion process uses something called the Seebeck effect. It works like this. You take two pieces of metal made from different materials. You join them at both ends to form a closed loop. If you heat one of those junctions and keep the other one cold, a voltage develops across the circuit. Electrons begin to flow. You get electricity. That temperature difference between the hot junction and the cold junction is what drives the entire system. In an RTG, the hot junction sits against the plutonium. The cold junction faces out toward space. And space, as we established in the previous section, is extraordinarily good at staying cold. The temperature differential is large. The current flows. The spacecraft gets power. No turbines. No pumps. No fuel being burned. Just a temperature difference and two dissimilar metals, converting heat into electricity through a principle discovered by a physicist named Thomas Seebeck in 1821. Now consider what happens to that power output over time. Plutonium-238 has a half-life of 87.7 years. That means it takes 87.7 years for half of the plutonium atoms in any given sample to decay. After 87.7 years, you have half the original material still remaining, still decaying, still producing heat. After another 87.7 years, you have a quarter. The decay proceeds slowly and on a completely predictable schedule. Voyager 2 has been flying for about 47 years. That's roughly 54% of one half-life. So the spacecraft has lost a little more than a quarter of its original power output to decay. From 470 watts at launch down to something closer to 200 watts today. The loss is real. It matters enormously. But it happened gradually, across decades, giving engineers time to adapt. That rate of decline works out to roughly 4 watts per year. Every single year without fail, Voyager 2 gets a little dimmer. 4 watts doesn't sound like much, but over 47 years it adds up to nearly 190 watts of lost capacity. That is a steep decline from the original 470. And every watt matters when you're running a spacecraft on a power budget that was already tight to begin with. mission engineers have spent years carefully rationing what remains, making decisions about which instruments get power and which ones go dark. But the fact that there is still power at all, that the spacecraft is still functioning, is a testament to how well chosen plutonium-238 was as a fuel source. A material with a shorter half-life would have exhausted itself decades ago. A material with a longer half-life would decay too slowly to produce enough heat. Plutonium-238 is almost ideally suited to exactly this kind of decades-long deep space mission. Now think about what the alternative would look like. What if the engineers had designed Voyager 2 with solar panels instead? It seems like a reasonable idea. Solar panels are clean and lightweight, and they worked well on spacecraft closer to the sun. The problem is the inverse square law. Sunlight intensity drops with the square of distance. Double your distance from the sun, you get 1/4 the light. Triple it, 1/9. At Voyager 2's current distance of roughly 12 billion miles, the sun is not the warm yellow star you see from Earth. It's a point of light. Brighter than other stars, yes, but barely. The amount of solar energy reaching Voyager 2 is approximately 0.001% of what reaches Earth. Solar panels large enough to be useful at that distance would need to be the size of a city block. It was never a realistic option. The RTG wasn't a compromise. It was the only solution that actually worked across the timescales and distances involved. There is something genuinely remarkable about the simplicity at the core of this design. A piece of radioactive metal sits inside a container. It decays. It produces heat. That heat passes through a pair of dissimilar metals. A current flows. A spacecraft on the edge of interstellar space powers its instruments, aims its antenna, fires its thrusters, and calls home. No combustion, no moving parts. No sunlight required. The same process happening inside every RTG sphere today is the same process that was happening 47 years ago. It cannot stop until the plutonium runs out, and the plutonium won't run out, not for centuries. What will happen instead is that the decay rate will slow enough that the electricity produced is no longer sufficient to run the spacecraft's systems. But the heat will continue. The decay will continue. Long after Voyager 2 goes silent, the plutonium at its core will still be releasing warmth into the void. It is, in a very real sense, a nuclear-powered campfire that has been burning for nearly half a century in the darkness between the stars. Electricity is only half of what the RTGs give Voyager 2. The other half is heat, raw, continuous, unavoidable heat that radiates outward from 3 plutonium cores and flows through the spacecraft's structure in carefully planned pathways. That heat isn't a side effect. It isn't waste in any meaningful sense of the word. It is, for Voyager 2, the difference between a functioning spacecraft and a frozen piece of metal drifting silently through interstellar space. To understand why heat matters so much, you have to understand what happens when a spacecraft gets cold. Not cold in the way we experience it on Earth, cold in the way that interstellar space is cold. Without any internal heat source, Voyager 2's components would eventually equilibrate with their surroundings. Metal contracts, seals crack, fluids freeze, and one fluid in particular would end the mission completely if it ever froze. That fluid is hydrazine. Voyager 2 carries a tank of hydrazine monopropellant. It's the fuel that powers the small attitude control thrusters dotted around the spacecraft's frame. These thrusters fire in brief, precise pulses. They nudge the spacecraft. They keep it oriented. They point the high-gain antenna toward a target 12 billion miles away that the spacecraft cannot see. Without those thrusters, Voyager 2 can't aim. Without aim, its 22-watt transmitter broadcasts into empty space. The signal never reaches Earth. The mission ends, not with a final data burst, but with silence. The hydrazine lines running from the tank to the thrusters are narrow. They're vulnerable. If those lines freeze and crack, there's no repair crew. There's no maintenance window. There's no contingency beyond total loss. The spacecraft would continue traveling, but it would be deaf and mute. Engineers on the ground would send commands and receive nothing back. So keeping those lines liquid isn't a secondary concern. It's one of the most fundamental survival requirements of the entire mission. RTG waste heat is what keeps them liquid. The 3 generators aboard Voyager 2 don't convert all of their thermal energy into electricity. They can't. The thermocouple technology used in the RTGs is efficient by the standards of deep space power systems, but a significant fraction of the heat produced by plutonium decay flows through the spacecraft structure without ever becoming electricity. Early in the mission, when the RTGs were running at full output, that thermal energy was substantial. It warmed the spacecraft bus. It kept instruments within operating ranges. It maintained the hydrazine at temperatures well above freezing. The spacecraft's thermal design was built around this reality from the beginning. Engineers at JPL in the early 1970s understood that Voyager would travel into regions of space far beyond the reach of sunlight. Solar panels were never seriously considered for the outer solar system missions. The sun at Jupiter is already 25 times dimmer than it appears from Earth. At Voyager 2's current distance, sunlight is essentially nothing. A few milliwatts per square meter, useless for power, and equally useless for warmth. So the thermal architecture of the spacecraft relies on passive control wherever possible. Passive means no moving parts, no pumps circulating coolant, no fans, no active heating elements that require their own electrical supply. Instead, the design uses insulating blankets wrapped around critical components, carefully chosen surface materials that control how much heat the spacecraft radiates away to space, and structural pathways that conduct waste heat from the RTGs toward the parts of the spacecraft that need it most. The goal was to create a system that would manage temperature automatically, without requiring commands from Earth, without consuming extra power, and without relying on mechanical systems that could wear out over decades. Think about what that requirement actually means. The engineers designing Voyager in the 1970s were building a spacecraft that had to stay warm on its own, without any assistance, for a time frame nobody was willing to put a firm number on. The official mission was Jupiter and Saturn, but the thermal design had to survive whatever came after, because nobody was certain the mission would end at Saturn. The passive thermal control system they built has now kept critical components within functional temperature ranges for nearly 50 years. That is an extraordinary achievement by any measure, but the system is not perfect, and it was never designed to last forever. As the RTGs slowly lose power, they also lose heat output. The two are inseparable. Plutonium-238 decays at a fixed rate. Less plutonium means less decay. Less decay means less heat reaching the thermocouples. Less heat at the thermocouples means less electricity, but it also means less waste heat flowing through the spacecraft. The thermal budget and the power budget decline together. The reality is that the passive thermal control system works well only within certain parameters. Temperature variations across different sections create distinct zones of vulnerability. Some areas maintain adequate warmth, while others edge steadily closer to minimum operating thresholds. Engineers monitor dozens of temperature sensors distributed throughout the entire spacecraft structure. Each sensor provides crucial real-time data about how heat actually flows. The detailed comparison between predicted thermal models and actual sensor readings reveals the true operational margins. Those margins grow progressively narrower each year as plutonium continues its unavoidable decay. This is where mission engineers face a genuinely difficult problem. When an instrument gets shut down to conserve power, that instrument stops drawing electricity, but it also stops generating its own small contribution to the spacecraft's internal heat. Every active instrument dissipates some energy as heat. Over time, as instruments go offline one by one, the spacecraft gets slightly colder from the inside. The RTG waste heat has to carry more of the burden alone. And the RTGs themselves are weaker than they used to be. The engineers have to balance these two concerns simultaneously. Shutting down an instrument saves power, which extends the mission, but it also removes a heat source, which stresses the thermal system. The calculus isn't straightforward. The decisions require detailed thermal modeling of the spacecraft at each new configuration, estimating how heat will flow through the structure after each change, checking whether the hydrazine lines will remain safely above their freezing point with one fewer instrument generating heat. These aren't abstract calculations. If the model is wrong and the lines freeze, the mission ends. So far, the models have been right. The hydrazine has stayed liquid. The thrusters have continued to fire. The antenna has continued to point toward Earth. But as the RTG output continues its slow, predictable decline, the margin between safe operation and catastrophic freezing grows narrower each year. What was once a comfortable thermal buffer has become something that engineers monitor carefully and continuously. There's something striking about this situation. The same process that generates Voyager 2's electricity is also generating its warmth. The same radioactive decay that powers the instruments keeping the mission scientifically alive is also protecting the mechanical systems that keep the mission physically alive. You can't separate the two functions. They come from the same source. The warmth keeping those fuel lines liquid is the same warmth that keeps the spacecraft pointed at Earth, which is the same warmth that keeps the mission alive. Every year, without exception, Voyager 2 gets a little dimmer. The RTGs that power the spacecraft are not failing. They are doing exactly what physics says they must do. Plutonium-238 decays at a fixed, predictable rate. The half-life is 87.7 years. That means roughly every 87 years the heat output drops by half. After nearly 50 years of operation, the RTGs have lost somewhere around a third of their original output. At launch, the three generators together produced about 470 watts of electrical power. That number has been falling ever since, dropping roughly 4 watts every year. That is less than 1% annually. But 1% compounding across 5 decades adds up. The spacecraft that was once managing 470 watts is now managing something closer to 260. Think about what 4 watts actually means. A single dim incandescent nightlight. That is the annual loss. And yet that tiny annual loss has driven some of the most consequential decisions in the history of the mission. The instruments aboard Voyager 2 are not passive devices. Each one draws power continuously. Each one generates some heat. Running all of them simultaneously stopped being an option years ago. Mission engineers at JPL have spent decades working through a slow, methodical triage, deciding which instruments stay on and which ones go dark. Some were shut down in the 1990s. Others survived into the 2000s and 2010s. By early 2023, 5 science instruments were still operating. Then, in October 2024, the plasma science instrument was turned off. That particular shutdown carried real weight. The plasma science instrument was the device that confirmed Voyager 2's crossing into interstellar space back in 2018. It was the instrument that made Voyager 2 uniquely valuable compared to Voyager 1, which had crossed the Heliopause years earlier with its own plasma detector non-functional. For 6 years after the crossing, That instrument had been sending back direct measurements of the interstellar medium. Turning it off meant losing the only functioning plasma detector humanity has ever placed in interstellar space. The decision was not made lightly, but the power budget left no other choice. The cosmic ray subsystem is scheduled to follow. Its shutdown is currently planned for 2026. After that, the remaining instruments will be assessed one by one, with the goal of keeping at least one science instrument operational into the 2030s. That goal is not guaranteed. It is a target that requires everything to go right. No unexpected component failures, no attitude control anomalies, no surprises from systems that are now pushing 50 years of continuous operation. Here is where the story takes an unexpected turn. A few years ago, engineers working through Voyager 2's power budget discovered something they hadn't counted on. The spacecraft carries a small onboard safety mechanism, a voltage regulator designed to protect instruments if the electrical output fluctuates outside a safe range. That safety buffer had been set aside at launch and never touched. It was not technically power generation. It was a reserve. Engineers realized they could carefully tap into it. Redirecting that reserve into the science systems meant the spacecraft could run its remaining instruments longer than the previous projections allowed. The addition bought the mission additional years. It is a remarkable find. After nearly half a century, a spacecraft launched in 1977 still had room to surprise the people caring for it. The reserve was not large, but at this stage of the mission, every watt matters. Every additional month of data from interstellar space is irreplaceable. The discovery extended the timeline. It meant instruments that would have been shut down earlier stayed on longer. It meant measurements that would have been missed were taken. What these power decisions feel like from the inside is harder to describe. Every instrument on Voyager 2 has been working correctly. The plasma science instrument did not break. The cosmic ray subsystem is not malfunctioning. These are healthy, functional scientific tools built with extraordinary care by teams of engineers and scientists in the 1970s. They have been operating continuously for close to 5 decades. Shutting them down is not a response to failure. It is a deliberate choice to accept a loss in scientific capability in order to preserve the spacecraft itself. The mission trades its own eyes and ears for the chance to keep existing a little longer. There is something genuinely strange about that trade-off. The instruments are the reason the mission exists. The whole purpose of sending Voyager 2 to interstellar space was to gather measurements that could not be taken from anywhere else. As those instruments go quiet one by one, the mission shrinks. What was once a suite of 5 functioning science tools becomes 4, then 3, then eventually 1. Each shutdown is a small, permanent loss. The data those instruments would have gathered is gone. No future mission can go back and collect it. And yet each shutdown is also what makes the rest of the mission possible. Without the conservation of power that comes from turning off the plasma science instrument, the remaining instruments cannot stay on. The math is unforgiving. There is no other source of energy. The RTGs are producing what they produce, and not a watt more. Every system aboard the spacecraft draws from that fixed and shrinking supply. Keeping one thing running means something else has to stop. Engineers have lived with this calculation for years. The teams working on Voyager 2 today did not build the spacecraft. Many of them were not yet born when it launched. They inherited the mission from the people who came before them, specialists who spent careers learning the quirks and behaviors of a 1970s-era spacecraft that was never meant to still be operating. The institutional knowledge required to manage Voyager 2 now is itself extraordinary. Understanding how its systems interact, how its power budget fluctuates, how its aging components respond to commands, none of that knowledge exists in a textbook. It lives in the people who have been working on this mission for years or decades. What they are managing now is not exploration in the way the mission once was. Voyager 2 is not racing towards something new. It is enduring. It is holding on. And the engineers holding on with it are making choices that will shape the final chapter of a mission that has lasted longer than almost any scientific program in history. Every instrument they turn off extends the life of those that remain. Every year of declining power output narrows the options. Every decision made in Pasadena today ripples forward into whatever time the spacecraft has left. Engineers who have spent their careers keeping Voyager 2 alive are now making the decisions that will determine exactly when it finally goes quiet. The reason scientists fought so hard to keep Voyager 2's instruments running isn't nostalgia. It isn't sentiment. It's because Voyager 2 is returning data that cannot be obtained any other way, from a place no other instrument has ever reached with the right equipment to measure it. When Voyager 2 crossed the Heliopause in November 2018, its plasma science instrument was still functional. That matters enormously. Voyager 1 had crossed the Heliopause years earlier, in 2012, but Voyager 1's plasma science instrument had failed back in 1980. It crossed the boundary essentially blind to one of the most critical measurements scientists needed. Voyager 2 crossed the same boundary with its plasma detector working. For the first time in history, scientists had a direct in-situ measurement of plasma conditions on both sides of the heliosphere's outer edge. What those measurements revealed was not what the models had predicted. The interstellar plasma near Voyager 2 is hot, extraordinarily hot. Measurements put the temperature somewhere between 30,000 and 50,000 Kelvin. Think about that for a moment. Prior models and observations had predicted temperatures in the range of 15,000 to 30,000 Kelvin. The reality came back nearly double the upper end of those estimates. 50,000 Kelvin is hotter than the surface of many stars. It is hotter than the surface of our own sun, which sits at roughly 5,500 degrees Celsius. The interstellar medium, that vast region between the stars, the place we had long imagined as a cold and empty void, is filled with plasma at temperatures that would be considered extreme by almost any standard. The numbers were so far outside expectations that scientists had to examine the data carefully before concluding it was real. And yet, as we've established, Voyager 2 isn't being cooked alive out there. The plasma is incredibly sparse. Temperature measures the average energy of individual particles, not the total energy available for transfer. When the particle density is low enough, even extraordinarily hot plasma transfers almost no heat to anything passing through it. But that makes the measurement no less significant scientifically. It tells us that our theoretical models of the interstellar medium had something wrong. Something is heating that plasma to temperatures our equations didn't predict. Understanding what that something is remains an open question. The significance of this finding extends beyond the immediate puzzle of heating mechanisms. These temperature measurements serve as a crucial constraint on theories about particle acceleration in astrophysical environments. When charged particles move through turbulent plasmas, they can gain energy through various processes. Understanding the baseline temperature of the interstellar medium helps scientists isolate which mechanisms are actually operating there. It also informs our understanding of similar transitions around other stars. If other stars have heliospheres, which they almost certainly do, they may show similar temperature anomalies at their boundaries. The data from Voyager 2 provides a template for what to expect when humanity eventually studies other stellar systems up close. For now, this single measurement represents humanity's only direct probe of these conditions. There was another surprise waiting just beyond the heliopause. The plasma density on the interstellar side of the boundary is actually higher than the plasma density inside the heliosphere. this is counterintuitive. Inside the heliosphere, the solar wind is a constant outward pressure, material away from the sun in all directions. You might expect the region just inside that bubble to be denser than what lies outside, but the measurements showed the opposite. The interstellar medium presses back against the heliosphere. Just beyond the boundary, the plasma is more concentrated than what Voyager 2 had been traveling through for years. This finding reshaped thinking about the pressure balance between the solar wind and the interstellar medium, about what physically sustains the heliosphere's shape and size over time. The boundary itself turned out to be more complex than a clean dividing line. Voyager 2 found itself in what researchers describe as a perturbed transitional zone. It had crossed the heliopause measurably and definitively, but the region beyond that crossing showed signs of ongoing mixing between solar and interstellar material. Solar particles were leaking outward through the boundary. Interstellar particles were finding their way inward. The heliopause is not a sealed wall. It is more like a membrane with imperfect edges, where material from both sides seeps through in small amounts. One analogy that emerged from the research described it this way: if the heliosphere were a ship, the hull would be slightly leaky. This wasn't a catastrophic finding. It just meant the boundary is dynamic rather than static, shaped by turbulence and pressure variations that vary over time. When scientists compared Voyager 2's crossing data with what Voyager 1 had measured at its crossing, differences emerged. The two spacecraft did not cross the heliopause at the same distance from the Sun. Voyager 1 crossed at about 121 astronomical units. Voyager 2 crossed at roughly 119 astronomical units. That gap is small, but the two spacecraft crossed in different directions. Voyager 1 is traveling roughly northward relative to the plane of the solar system. Voyager 2 is traveling southward. The fact that the crossing distances were different in these two directions tells us something about the shape of the heliosphere itself. The boundary is not a perfect sphere. It is asymmetric. The Sun is not sitting still at the center of a uniform bubble. The Sun moves through the galaxy. That ocean distorts the heliosphere, compressing it on the leading side and stretching it on the trailing side. The difference between the two crossing distances reflects that asymmetry in a way that can now be measured rather than just theorized. This comparison between the two spacecraft is one of the more remarkable aspects of the Voyager mission. We essentially conducted the same experiment twice, 40 years apart, at two different points on the heliosphere's outer surface. The results were similar enough to validate each other and different enough to reveal something new. No single crossing point could have told us that the boundary was asymmetric. It required both spacecraft, traveling in different directions, measuring the same transition at different distances, for that conclusion to become possible. What all of this adds up to is a picture of the heliosphere and the interstellar medium that is more complicated and more interesting than our pre-Voyager models suggested. The boundary is not clean. The temperatures beyond it are higher than expected. The densities are structured in unexpected ways. The solar wind doesn't simply stop at the heliopause and let the universe begin. There is a transition, a negotiation between the two environments, playing out across a region of space that is itself enormous by any human measure. Every piece of that picture required direct measurement from inside interstellar space to confirm. Theoretical models can predict. Remote observations can suggest. But at some point, you have to go there. And here is where the uniqueness of Voyager 2's position becomes impossible to overstate. Its plasma science instrument is the only functioning plasma detector humanity has ever placed beyond the heliosphere. There are no plans to send another mission to interstellar space anytime soon. The next probe designed to reach the heliopause and cross it won't be launched for years. It would take decades after launch to reach the boundary. Everything we know about the direct plasma environment of interstellar space, every in-situ measurement, every data point that required an instrument actually present in that region to collect, comes from Voyager 2. There is no backup source. There is no redundancy. There is no other dataset to cross-reference against. There is no telescope on Earth, no satellite in orbit, no probe anywhere in the solar system that can tell us what Voyager 2 can tell us. This was because none of them are out there. When engineers in Pasadena send a command to Voyager 2, they wait, not minutes, not an hour. They wait 18 hours just for the signal to arrive. Then they wait another 18 hours for any response to come back. A full day and a half passes before they know whether a single command worked. That is the reality of communicating with something 12 billion miles away. Radio signals travel at the speed of light. That sounds fast. Light crosses the entire diameter of Earth in less than 1/10 of a second. It travels from the moon to your eye in about 1.25 seconds. From the sun to Earth, it takes roughly 8 minutes. But from Earth to Voyager 2, light takes around 18 hours. One way. The universe is not small, and Voyager 2 has done more than almost anything else in human history to make that felt. This is not a problem you can engineer your way around. The speed of light is the speed of light. No antenna makes it faster. No software shortcut closes that gap. The delay is physics, and it is absolute. So when something goes wrong with Voyager 2, engineers cannot simply reach out and fix it in real time. They have to diagnose the problem from 12 billion miles away, write a command sequence, send it, and then wait 36 hours minimum to find out if their solution worked. Every decision carries that weight. The antennas doing this work belong to NASA's Deep Space Network. It is a system of giant dish antennas stationed at 3 locations around the globe: Goldstone in California, Madrid in Spain, and Canberra in Australia. The 3 sites are spaced roughly 120 degrees apart in longitude. As Earth rotates, at least one of them is always facing the direction of Voyager 2. The largest dishes in the network stretch 70 meters across. That is about 230 feet in diameter. They are among the most sensitive radio receivers ever built, and they have to be, because the signal they are trying to catch is almost nothing. Voyager 2 transmits with 22 watts of power. A standard household light bulb uses more electricity than that. A laptop charger uses more than that. 22 watts, broadcast in every direction from a point 12 billion miles away. By the time that signal crosses that distance and arrives at Earth, the power level has dropped to something around 10 to the negative 16 watts. That is 0.0000 0000 0001 watts. The number is almost meaningless to write. It represents a signal so faint that it contains less energy per second than a single falling snowflake makes on contact with the ground. Extracting actual scientific data from something that faint is an extraordinary engineering problem. The dishes must be pointed with extreme precision. The receivers must be cooled to near absolute zero to reduce thermal noise that would otherwise drown the signal entirely. Multiple antennas can be linked together and their signals combined, a technique called arraying, which effectively creates a larger virtual dish. Signal processing algorithms filter out interference and reconstruct the original transmission from what would otherwise be indistinguishable from background noise. Even then, the data rate is slow. Voyager 2 sends back data at roughly a few hundred bits per second. A modern home internet connection transfers millions of times more data per second. But those few hundred bits contain measurements from interstellar space that no other instrument can provide. And none of that works if Voyager 2 is not pointing at Earth. This is where the thermal problem and the communication problem connect. Voyager 2 uses attitude control thrusters to maintain its orientation. Those thrusters run on hydrazine fuel. The hydrazine must remain liquid to flow, and it stays liquid because of waste heat from the RTGs. If that heat ever fails, the fuel lines freeze, the thrusters stop firing, and the antenna drifts away from Earth. The signal disappears. So the ability to communicate at all depends on the thermal chain staying intact across all 12 billion miles. The spacecraft cannot see Earth. It has no camera pointed back at its origin. It navigates its orientation using gyroscopes and star trackers, locking onto known reference stars to determine its attitude in space. From that, it calculates where Earth should be and points accordingly. It does this autonomously. The engineers on the ground can send updated pointing instructions, but the spacecraft must execute them on its own, interpreting commands that were written 18 hours earlier based on conditions that may have shifted. The relationship between mission controllers and the spacecraft is therefore not a conversation in any familiar sense. It is something more like leaving instructions for someone you cannot reach, than waiting to see what they found. This autonomy was necessary from the beginning, but it has become increasingly precious now. No human operator could manage the communication delay in real time. The spacecraft must decide for itself whether a command makes sense, whether its sensors match the expectations embedded in that old instruction set. It must diagnose its own problems within the constraints of half a century of aging hardware. It must keep itself pointed at Earth, keep itself warm, keep itself alive. The engineers watch and advise, but the spacecraft carries the actual responsibility. It is a partnership stretched across an unimaginable distance where trust has been baked into the machine's very code. There have been moments when that relationship came close to breaking. In 2020, Voyager 2 briefly went into fault protection mode and stopped transmitting science data. Engineers spent months working to restore full contact, sending commands and waiting days at a time to see what had changed. The process required patience at a scale most people never encounter in their professional lives. Eventually, they succeeded, but the episode illustrated how fragile the thread really is. One wrong command, one unanticipated response from the spacecraft, and the recovery process stretches across weeks. What is strange about all of this is the intimacy it creates despite the distance. The engineers who work the Voyager mission know the spacecraft the way a doctor knows a long-term patient. They know its quirks, its weaknesses, the particular way it responds to certain commands. They know which systems are most reliable and which ones require care. They know the spacecraft's history in detail because they have to. There is no manual current enough to cover 50 years of accumulated drift and change. The relationship between this team and this machine is unlike almost anything else in human experience. A machine built before most of its current caretakers were born, still responding, still obeying, still returning data from a place no instrument has ever been before. Every day, the Deep Space Network dishes point toward the outer solar system and wait. The signal comes in, faint beyond description, crossing a distance that takes light 18 hours to traverse, emerging from a region that no human being has ever experienced firsthand. And the dishes catch it, and the processors clean it, and the data arrives. A 22-watt signal crossing 12 billion miles of space, arriving at a dish in the Australian desert, carrying news from somewhere no human has ever been. Voyager 2 was not supposed to still exist. When engineers at the Jet Propulsion Laboratory assembled the spacecraft in the early 1970s, the mission plan was straightforward. Fly past Jupiter, fly past Saturn, gather data. End of mission. That was the full scope of what anyone was officially promising. The spacecraft was built to survive a few years in space, not 5 decades. Not interstellar travel. Not a journey beyond the edge of the solar system to a place no human instrument had ever been. The technology inside Voyager 2 reflects the era that produced it. The onboard computers operate with roughly 69 kilobytes of memory. A modern smartphone carries billions of times more processing power. The integrated circuits are primitive by any current standard. The data transmission rate is measured in bits per second, not megabytes. Every component was cutting edge in 1977, and every component would look like a museum exhibit today. And yet this collection of 1970s hardware is currently operating in interstellar space, more than 12 billion miles from the people who built it. Still returning data, still following commands, still working. Think about what 1977 actually meant in terms of technology. The first personal computer had barely arrived. The concept of the internet didn't exist for most people. A pocket calculator was a serious piece of equipment. Engineers were designing Voyager 2 using slide rules alongside early digital tools, drawing schematics by hand, testing components in ways that would seem almost unimaginably labor-intensive today. The spacecraft they produced weighed about 1,600 pounds. It was roughly the size of a small car, and it has now been operating continuously for 48 years. The original mission didn't include Uranus or Neptune. That part came later, and it came because of something remarkable happening in the outer solar system. The giant planets, Jupiter, Saturn, Uranus, Neptune, were aligning in a configuration that only occurs once every 175 years. This alignment made a gravity assist trajectory possible, where a spacecraft could swing past one planet, gain speed from its gravitational pull, and be flung toward the next. Without this alignment, visiting all 4 planets in a single mission would require vastly more fuel than any spacecraft could carry. The window to take advantage of it was narrow. NASA took it. The extended mission required Voyager 2 to survive far longer than its original design anticipated. Systems had to keep functioning through radiation belts, extreme temperature swings, and years of deep space travel between encounters. Jupiter came in 1979, Saturn in 1981, and then the spacecraft kept going. Uranus in 1986, Neptune in 1989. Each flyby returned data that transformed what scientists understood about those worlds. The rings of Uranus, the moons of Neptune, the geysers of nitrogen erupting from the surface of Triton. Voyager 2 discovered things that no mission before it had seen, at worlds that no mission after it has visited. To this day, Voyager 2 remains the only spacecraft ever to have flown past Uranus or Neptune. Not the only one to have done it well, the only one to have done it at all. After Neptune, the spacecraft had no more planetary destinations. It was heading outward, away from everything, into the long dark stretch between the solar system and whatever lay beyond it. There was no scientific reason to expect it would survive another decade, let alone 3 more. But the RTGs kept producing power. The systems kept functioning. The antenna kept pointing home. And mission controllers kept sending commands, kept listening, kept learning. The power systems that kept Voyager 2 functioning represent another engineering marvel. The spacecraft relies on radioisotope thermoelectric generators that convert radioactive heat into electrical power. These units were built to provide diminishing power over decades by engineers who anticipated a long but finite mission. They didn't fully foresee that the mission would continue so far that power decline would become a constant operational constraint. Year after year, as RTGs weakened, engineers had to decide which instruments to shut down to preserve power for essential communication functions. There is something genuinely strange about the 48-year operational record. The engineers who designed Voyager 2's core systems were working in their 30s and 40s when the spacecraft launched. Many of them have retired. Many of them have died. The spacecraft has outlasted careers, outlasted institutions in their original forms, outlasted entire generations of the technology it was built with. The people who understood its systems most deeply at the time of launch are no longer available to answer questions. Their knowledge lives on in documentation, in the memories of colleagues who trained under them, in the institutional knowledge that JPL has worked hard to preserve. But the original builders are largely gone, and the spacecraft they built is still out there. That gap between creator and creation is almost impossible to fully appreciate. When Voyager 2 launched in August of 1977, no one in the world carried a device in their pocket capable of accessing the sum of human knowledge. The moon landings were still fresh, the Cold War was at full intensity, and a team of engineers built a spacecraft with the tools available to them, knowing they were doing something no one had done before, not fully knowing how long it would last or what it would find. What it found exceeded every original expectation, and what it is still finding, even now, still adds to the scientific record in ways that no other instrument can replicate. The heliosphere boundary data that Voyager 2's plasma science instrument gathered before it was shut down in 2024 was irreplaceable. The measurements of interstellar plasma density and temperature came from the only functioning plasma detector humanity has ever placed in interstellar space. None of that was possible in 1977. None of it was planned. It happened because the spacecraft survived long enough to get there. Engineers like to build things that work. The deeper aspiration, the one that doesn't always get said aloud, is to build something that keeps working long after anyone expected it to. Voyager 2 is the clearest example in the history of spaceflight of that aspiration being realized beyond any reasonable measure. It was built to last a few years. It has lasted nearly 50. It was built to visit 2 planets. It visited 4. It was built to operate inside the solar system. It operates in interstellar space. The people who built Voyager 2 could not have known they were building something that would still be working when most of them were gone. Right now, at this moment, Voyager 2 is operating in what NASA calls survival mode. That phrase is worth sitting with. Survival mode. Not science mode, not exploration mode. Survival. The spacecraft that flew past Jupiter, past Saturn, past Uranus and Neptune, that crossed the boundary of the solar system and entered interstellar space, it is now focused on one thing: staying alive long enough to keep talking. What survival mode looks like in practice is a careful, relentless prioritization of everything aboard the spacecraft. Thrusters fire as infrequently as possible. Each burn uses hydrazine fuel, and every drop of that fuel is irreplaceable. The spacecraft maneuvers only when it has to, only when the antenna needs to be reoriented toward Earth or an instrument needs to be repositioned. Between those moments, Voyager 2 holds its position and drifts. It generates heat from its RTGs, it routes that heat to critical systems, and it waits. The spacecraft that once moved with purpose through the outer planets now moves with patience through the dark between the stars. Through early 2023, 5 science instruments were still operating. That number has since dropped. In October 2024, NASA shut off the plasma science instrument. That instrument had been one of the most valuable tools aboard, the very detector that recorded the Heliopause crossing in 2018, the one that measured the shift from solar wind plasma to interstellar medium. Turning it off wasn't a technical failure. It worked perfectly. It was shut down because the RTGs no longer produce enough power to run everything, and a choice had to be made. The cosmic ray subsystem is scheduled to follow in 2026. Each shutdown is not a malfunction, it's a decision. The instruments that remain active were chosen for specific reasons. The measurements they provide cannot be made from anywhere else. No telescope, no satellite, no probe inside the solar system can directly sample the interstellar medium. Only Voyager 2 is out there. So the instruments that survive the cuts are the ones measuring things no one else can measure. Magnetic fields, low-energy charged particles, the faint electrical properties of the plasma surrounding the spacecraft. These are the readings that tell scientists what the space between the stars is actually made of, how it behaves, how it varies. Every day those instruments remain on. They are adding to a dataset that is, by definition, unique in the history of human science. Think about what that means. A spacecraft operating on backup power, at the edge of its thermal limits, billions of miles beyond the last planet, is still producing data that cannot be replicated by any instrument on Earth or in orbit. It is not a relic running on sentiment. It is an irreplaceable observatory that happens to be running out of time. The people keeping it alive are in some ways just as remarkable as the machine itself. At JPL, there are engineers who have spent their entire professional careers on the Voyager missions. Not the early years, not the planetary flybys, the long, quiet middle of the mission, the decades of cruise phase, the careful monitoring of a spacecraft growing steadily more distant and more fragile. These are specialists in systems that no longer exist anywhere else. The computers that run Voyager 2 use instruction sets that are decades obsolete. The programming languages are no longer taught. The documentation, in some cases, exists only in aging binders or in the memories of people who wrote it themselves. When a senior engineer retires from the Voyager team, something genuinely difficult happens. Knowledge walks out the door, not knowledge that can be easily transferred from a textbook or reconstructed from first principles. Operational knowledge, the kind that says, when this happens, do that. Because 40 years ago we learned what happens if you don't. The kind of knowledge that lives in experience, not documentation. Replacing it requires deliberate, sustained effort, pairing new engineers with veterans before those veterans are gone, recording conversations, preserving institutional memory in whatever form it can be captured. Some of the engineers who designed the original systems have died. Others retired years ago. The people maintaining Voyager 2 today are working with systems they didn't build, in some cases maintaining hardware older than they are, guided by manuals written before they were born. There is something almost archaeological about it, a kind of technical archaeology, sifting through decades of accumulated knowledge to keep a machine alive that was never supposed to last this long. And yet, it has lasted. It is lasting right now. Somewhere beyond the edge of the heliosphere, moving at roughly 34,000 miles per hour through interstellar space, Voyager 2 is warm enough to function, powered enough to transmit, oriented precisely enough to send a signal across 12 billion miles, and have it arrive at an antenna dish in the Australian desert. That does not happen by accident. It happens because a small group of people has refused to let it stop. They manage power budgets down to single watts. They monitor temperatures down to single degrees. They consider every thruster firing before approving it. The margin for error is almost nothing, and they operate within that margin every single day. Survival mode is not failure. It is what succeeding looks like when the mission is 5 decades old and the laws of physics are slowly closing in. The spacecraft is enduring. So are the people who tend to it. The knowledge of how to keep Voyager 2 alive has been passed down like a craft tradition from one generation of engineers to the next across 5 decades. Sometime around 2030, the last instrument on Voyager 2 will power down. The RTGs have been losing roughly 4 watts of output every year. That's a slow decline, steady and predictable, but it adds up. After nearly 5 decades of continuous operation, the generators simply won't have enough output left to run science instruments and keep the spacecraft's critical systems warm at the same time. Engineers will face a choice with no good answer, and eventually there won't be a choice at all. The numbers will make the decision for them. Current projections put the final instrument shutdown somewhere around 2030. After that, NASA will likely send a formal shutdown command around 2035. That command will travel outward from Earth at the speed of light. It will take roughly 18 hours to arrive, and when Voyager 2 receives it and goes silent, the mission that began in August of 1977 will be over. Almost 60 years of continuous operation. No spacecraft in history has come close. Yet what tends to escape most people's attention is this reality. The mission ends. The spacecraft doesn't. After shutdown, Voyager 2 will keep moving. There's nothing out there to slow it down. No atmosphere, no friction, no gravitational drag significant enough to matter on any human timescale. It will travel at roughly 34,000 miles per hour relative to the Sun, on a trajectory that curves gently through the galaxy. It will never loop back, it will never return, it will just go. Think about that for a moment. The signals stop, the data stops. The relationship between the spacecraft and the humans who built it ends completely, and the object itself continues, silently, for millions of years. In fact, this distinction between mission and machine represents something profound about human engineering. We design our instruments to serve temporary purposes, to answer specific questions within specific time frames, yet the physical objects we send into space inherit a permanence we rarely contemplate. Once released beyond Earth's protective boundaries, they become something else entirely. Not tools anymore, but wanderers. Artifacts of human ambition frozen in their moment of launch, destined to exist long after the people who created them have disappeared. In about 40,000 years, Voyager 2 will make its closest approach to another star. That star is called Ross 248. It's a small red dwarf, unremarkable by most measures, located in the constellation Andromeda. Voyager 2 won't reach it. It will pass within about 1.7 light-years, close in galactic terms, but still an enormous distance. That's roughly 10 trillion miles at closest approach. The spacecraft will drift past and keep going. Ross 248 won't notice. Voyager 2 won't notice. But 40,000 years from now, it will be the nearest star that any human-made object has ever reached. 40,000 years. When Voyager 2 launched, humans had only been farming for about 10,000 years. The pyramids at Giza were roughly 4,500 years old. The entire span of recorded human history is only about 5,000 years. Voyager 2's closest stellar encounter is 8 times that duration into the future. Whatever human civilization looks like at that point, if it exists at all in any recognizable form, the spacecraft will still be moving through the dark between the stars. Aboard Voyager 2, there is a gold-plated copper disc. It's about 12 inches in diameter. It carries sounds and images from Earth, greetings in 55 languages, music from dozens of cultures, the sounds of wind and rain and surf, the sounds of a mother's first words to a newborn child. There are images of humans, of animals, of landscapes, of mathematics. There is a diagram explaining where Earth is in the galaxy and how to play the record. Carl Sagan called it a message in a bottle cast into the cosmic ocean. The golden record was never really designed for us. It was designed for whoever finds it, if anyone ever does. The odds are extraordinarily low. Space is almost unimaginably empty. The chance that any civilization anywhere ever intercepts this particular object is vanishingly small, but it's not zero. And for the scientists and artists who put it together, that was enough. The record is a statement. It says, "We existed. We were here. This is what we were like." What makes the golden record strange is that it will almost certainly outlast every single thing it represents. Every language spoken into its grooves, every nation whose music it carries, every institution that funded the mission that launched it. The copper disk, sealed in gold, tumbling slowly through interstellar space, will survive long after human civilization has transformed into something unrecognizable or disappeared entirely. In that sense, Voyager 2 isn't just humanity's most distant object. It may be humanity's most permanent one. Hundreds of millions of years from now, the sun will still exist. Earth may still exist, but every city currently standing on it will be gone. Every mountain range will have eroded. The continents will have moved into entirely different configurations. The species that built Voyager 2 will almost certainly not exist in its current form. And the spacecraft will still be moving through the Milky Way, carrying its gold disk, its plutonium cores long since cooled to inert metal, its antenna pointed at nothing in particular. There is something genuinely strange about building a thing that will outlast you so completely. The engineers who assembled Voyager 2 in a California factory in the early 1970s were building a machine they expected to last a few years, maybe a decade. It has lasted nearly 50, but the object itself, the physical hardware, doesn't need power to persist. It just needs to be in space, where nothing corrodes it, nothing weathers it, nothing pulls it apart. And in space, that condition holds for longer than we have words for. Every human artifact we've ever made, every book, every building, every monument exists somewhere on Earth, subject to erosion and time and catastrophe. Voyager 2 is the exception. It's beyond all of that. It's beyond weather, beyond geology, beyond anything Earth can do to it. It has escaped the planet in the most literal sense possible, and in doing so, it has escaped the fate of almost everything humanity has ever created. The mission ends around 2035. The last signal goes out. The last acknowledgement comes back, 18 hours later, and then silence. But somewhere beyond 12 billion miles, a spacecraft keeps moving, carrying a gold disc pressed with the sounds of a world it will never see again. Long after the last person who remembers Voyager 2's launch is gone, long after the languages carved onto its golden record are dead, the spacecraft will still be moving. It is worth stopping to think about the distance Voyager 2 has actually covered. More than 12 billion miles. That number gets repeated often enough that it starts to feel routine. 12 billion miles. We say it the way we say other large numbers, casually, as though we understand it. We don't. 12 billion miles is roughly 0.002 light years. In the language of the cosmos, that is almost nothing. But in any human frame of reference, it is a distance so extreme that our minds can't properly hold it. Here is one way to think about it. Light travels at 186,000 miles per second. It takes light about 8 minutes to travel from the sun to Earth. That same light, moving at that same incomprehensible speed, takes about 16.5 hours to reach Voyager 2. Not 16.5 minutes, 16.5 hours. A beam of light leaving the sun right now won't reach Voyager 2 until sometime tomorrow. And Voyager 2 has been moving continuously, without stopping, for nearly 50 years to get that far. Think about what 50 years of travel looks like at 34,000 miles per hour. That's faster than any bullet ever fired, faster than any aircraft ever built. Moving at that speed, You could circle Earth at the equator in about 44 minutes. In a single day, Voyager 2 covers roughly 800,000 miles. In a single year, it covers about 300 million miles. And after 47 years of that, after nearly 5 decades of constant motion through the solar system and beyond, it has crossed 12 billion miles. The nearest star system to our own is Alpha Centauri. It sits about 4.37 light-years away. At Voyager 2's current speed, traveling in a straight line toward it, which it isn't, it would take approximately 75,000 years to arrive. 75,000 years ago, modern humans were still carving tools from stone. There were no cities, no writing, no agriculture. The entire arc of recorded human civilization, every empire that ever rose and fell, every war ever fought, every language ever spoken, all of it would fit inside the travel time required to reach just the closest neighboring star at Voyager 2's speed. And Alpha Centauri is our nearest neighbor. It is, in astronomical terms, right next door. Beyond it, the distances only grow. The Milky Way stretches roughly 100,000 light-years from one edge to the other. Voyager 2, at its current speed, would need something like 1.7 billion years to cross it. The galaxy is not large in the way a country is large. It is large in a way that makes the word large feel inadequate. Voyager 2 has been traveling for nearly half a century, and it has covered 0.002 light-years. The Milky Way is 100,000 light-years wide. Do the math and what you get is humbling. Voyager 2 has covered roughly 200 millionths of the galaxy's diameter. That fraction is too small to have an intuitive name. What this tells us is something fundamental about the challenge of reaching other stars with conventional spacecraft. Voyager 2 is fast. It is the second fastest human-made object ever to leave the solar system. It uses no fuel for propulsion. It has been coasting on the momentum from its original launch and planetary gravity assists for decades. There is no realistic way to make a chemical rocket go much faster than Voyager 2 is going. And at that speed, the nearest star is 75,000 years away. This is the core problem of interstellar travel. It isn't engineering exactly. It isn't materials science or fuel chemistry. It's the sheer, almost hostile scale of the distances involved. The stars are not far in the way that distant cities are far. They are separated by voids so enormous that our fastest spacecraft look motionless against them. Consider for a moment the physics of a more ambitious approach. Even if we could somehow achieve velocities approaching half the speed of light, a feat that remains purely theoretical with any spacecraft we can currently conceive, the journey to Alpha Centauri would still require roughly 9 years. The energy requirements would be staggering. The technological barriers would be not just significant but potentially insurmountable with any foreseeable advances in propulsion. We don't have half-light speed spacecraft. We have Voyager 2, moving at 34,000 miles per hour. The gap between what we have achieved and what we would need to achieve for meaningful interstellar travel yawns open as impossibly as the distances themselves. Voyager 2's trajectory, for what it's worth, isn't aimed at Alpha Centauri. It's heading in a completely different direction, out through the constellation Telescopium. In about 40,000 years, it will pass within roughly 1.7 light-years of a small red dwarf called Ross 248. That's the closest encounter with any star on its entire projected path. 1.7 light-years. Still not close enough to be called an arrival. More of a distant pass. But here is what makes this all remarkable rather than simply discouraging. Voyager 2 got there. It got to interstellar space, a machine assembled by human hands in the 1970s, powered by decaying plutonium, guided by engineers using computers that would struggle to run a modern smartphone app. That machine crossed the boundary of our solar system. It left the heliosphere. It entered the space between the stars. No other scientific instrument humanity has ever built has done that with a functioning plasma detector. The fact that the distances are humbling doesn't diminish the fact that we crossed them at all. In 1977, the outer boundary of the solar system was a theoretical concept. We knew the heliosphere probably existed. We suspected there was a heliopause somewhere. We had no direct measurements of what interstellar space actually contained. Now we do, because Voyager 2 is there. It took 41 years to reach the crossing point. It covered 119 astronomical units, roughly 11 billion miles at that moment, before it passed through. And every mile of that distance was real. What the distance reveals, more than anything, is context. Context for why interstellar travel remains so far beyond our current capability. Context for why the Voyager missions represent both the pinnacle of what we have achieved and a sobering illustration of how small that achievement is against the scale of the galaxy. Context for what it means to be a technological civilization on a small planet orbiting an ordinary star in one arm of one galaxy among hundreds of billions. Voyager 2 has traveled farther than any object humanity has ever built, and it has barely left the neighborhood. The fact that anyone is still listening is itself remarkable. Voyager 2 is nearly 50 years old. Its computers have less processing power than a cheap digital watch. Its transmitter puts out 22 watts, about the same as a dim light bulb. And yet teams of engineers report to work every day with the specific purpose of keeping contact with this machine. Antenna time on NASA's Deep Space Network gets allocated to it. Budgets get approved for it. Careers get built around it. That doesn't happen by accident. It happens because the data coming back from Voyager 2 cannot be obtained any other way. There is no substitute for being there. That's the core of it. Telescopes can observe distant stars and map the structure of the galaxy from Earth. Satellites in orbit around the Sun can measure the solar wind, track magnetic fields, monitor the heliosphere from the inside. But none of those instruments are in interstellar space. None of them can take a direct measurement of the plasma that fills the space between the stars. Voyager 2 can. And right now, it's the only thing humanity has ever built that can do that from that location with working instruments. The measurements it returns are called in-situ measurements, direct, on-site readings taken from inside the environment being studied. When Voyager 2 measures the density of interstellar plasma, it's not inferring that density from the behavior of light passing through a distant medium. It's sampling the actual particles surrounding the spacecraft. When it measures temperature, it's measuring the energy of real particles in the actual interstellar medium. That kind of data is different in kind, not just degree, from anything an Earth-based observatory can collect. Models built entirely from remote observations have blind spots. Voyager 2 has been filling those blind spots, one data point at a time. Some of what it has found doesn't match what scientists expected. The interstellar plasma near Voyager 2 is hotter than models predicted. The plasma density just beyond the heliopause turned out to be higher than the plasma inside it. The boundary of the heliosphere appeared leaky, with solar particles trickling through into interstellar space. None of these things were supposed to be true according to the best theoretical frameworks available before Voyager crossed over. Each discovery forced a revision. Each revision made the models more accurate. That process is still happening. The instruments still running on Voyager 2 are still returning readings that scientists are still using to refine their understanding of how the Sun shapes the space around it and how the galaxy pushes back. That question matters more than it might seem. The heliosphere is not just a scientific curiosity. It is the environment our entire solar system moves through. It shields the planets from a significant fraction of galactic cosmic radiation. Understanding where that shield ends, how thick it is, how it responds to changes in solar activity, and how it interacts with the interstellar medium. These are foundational questions about the conditions that made life possible here, and about what conditions might exist around other stars. Voyager 2's measurements are directly relevant to those questions. It is not a relic sending back nostalgic signals from a forgotten era. It is an active scientific instrument operating in a region no other instrument can reach, and yet the scientific value alone might not be enough to explain why people are still listening. There's something else in this story, something harder to quantify. The decision to continue funding contact with Voyager 2 cannot be justified by cost-benefit analysis alone. Engineers working on the mission have developed a unique relationship with this instrument, one that clearly transcends the typical professional requirements of their jobs. Year after year, they arrive at their posts knowing the spacecraft could fail at any moment. Yet they show up without hesitation. They prepare the commands, they wait for the signals. This persistence suggests something more fundamental is at work than mere obligation. Think about what it means to maintain contact with a spacecraft for 5 decades. Engineers who were children when Voyager 2 launched are now leading the teams that keep it alive. The original engineers have mostly retired. Some are gone. The institutional knowledge of how to operate a 50-year-old spacecraft built with 1970s technology has been transferred painstakingly from one generation to the next. This is not a simple technical handover. The documentation is incomplete in places. The systems behave in ways that only become clear after years of working with them. There are people alive today whose entire professional purpose has been to understand and preserve a machine that most of the world has forgotten about. That level of dedication is not explained by budget line items or MISI. On objectives, it comes from something more personal than that. There is a deep human resistance to the idea of letting go of something that is still working. Voyager 2 has not asked to be abandoned. It responds to commands. It returns data. It is, by every measurable standard, still doing its job. The people maintaining it seem to take that seriously. As long as the spacecraft is still out there, still reachable, still capable of returning something useful, the conversation continues. That refusal to end the conversation, even when ending it would be administratively easier, even when the data volume is a fraction of what it once was, says something real about human nature. We build things and we become attached to them. We send something into the universe and we keep listening for its voice long after it has moved beyond any reasonable expectation of survival. Voyager 2 crossed the boundary of the solar system, and we followed it as far as we could with radio waves. It moved into the unknown, and we kept the line open. That's not engineering. That's something closer to loyalty. The spacecraft refuses to stop, and so do the people who built it. There is something worth sitting with at the end of all of this. The plutonium aboard Voyager 2 was not manufactured here on Earth. Not originally. The plutonium-238 in those 3 RTGs traces its origin back to a star that died long before our sun existed. A massive star that burned through its fuel, collapsed, and exploded. And in that explosion, heavier elements were forged and scattered into space. Eventually, some of that material drifted into the cloud that became our solar system. It settled into the Earth. We found it. We refined it. We pressed it into 72 small spheres and loaded them onto a spacecraft bound for the edge of everything. Humanity's farthest reach into the cosmos is literally powered by the ash of dead stars. Think about what that means. The same process that created Stevenson 218, that created UY Scuti, that creates every red supergiant that dwarfs our sun. That process is what keeps Voyager 2 alive out there. The stellar explosions that seeded the galaxy with heavy elements billions of years ago are the reason a spacecraft launched in 1977 is still functioning in interstellar space today. The fuel that heats those thermocouples, that generates those watts of electricity, that keeps those hydrazine lines from freezing, all of it came from a star we will never know the name of in a time before Earth existed. Voyager 2 was assembled by hand. Workers in a factory in California mounted instruments, connected wiring, tested systems. They torqued bolts and soldered circuits. They built something roughly the size of a small car and attached it to a rocket. The people who built it were born on this planet. They ate lunch and drove home and watched the news. They had no way to stand where Voyager 2 is now. No human has ever been there. No human ever will be, not in any foreseeable future. And yet the machine they built with their hands is out there, in a region of space our species has never touched, still sending signals back. There is a gold-plated copper disc aboard Voyager 2, the Golden Record. It carries sounds from Earth, waves on a shore, wind through trees, a human heartbeat, music from a dozen cultures. It carries images, greetings in 55 languages. It carries a map showing where Earth is in case something finds the spacecraft and wants to know where it came from. The record is not a scientific instrument. It collects no data. It measures nothing. It is simply an introduction. It says, "We were here. This is what we sounded like. This is where we lived." That record is now more than 12 billion miles from the people who made it. It is moving away from Earth at roughly 34,000 miles per hour. It will never slow down. It will drift through the galaxy for millions of years after every language on it has gone extinct, after every nation that contributed to it has dissolved, after the sun has changed beyond recognition, and it will still be carrying those sounds, a heartbeat from a species that may not exist anymore, traveling through interstellar space indefinitely. What is remarkable is not that we sent it. What is remarkable is that the spacecraft carrying it is still alive, still powered, still pointing its antenna back at a pale blue dot it left behind half a century ago. The RTGs are weaker now. The instruments are shutting down one by one. Engineers are making hard decisions about what gets to keep running and what gets turned off. But the spacecraft endures. The nuclear fire at its core is still burning. The signal is still crossing that impossible distance. Something is still answering. The signal traveling back from Voyager 2 is extraordinarily faint. By the time it reaches our antennas, it carries only a few watts of power, less electricity than a hearing aid consumes. The Deep Space Network's massive dishes in 3 locations around the world must work in concert to capture it. Engineers listen for this whisper across 12 billion miles of vacuum, reconstructing partial data from noise and celebrating when a transmission arrives intact. Each successful communication is a small victory against entropy itself. The journey of that signal mirrors the spacecraft's own journey, an improbable thing persisting across an impossible distance. The teams that monitor Voyager 2 have changed entirely since launch. A new generation has inherited stewardship of the mission. Yet year after year, decade after decade, the spacecraft reaches back. And year after year, we answer by listening. It is a conversation that began before most of the people currently tending to it were born. We tend to think of deep space as the place where things stop, where signals fade, where machines go silent. And eventually, that is true. Voyager 2 will go quiet. The RTGs will fall below the threshold. The last instrument will power down. The antenna will stop transmitting. But the spacecraft will not stop moving. It will coast through the galaxy, carrying its golden record, powered by nothing but inertia, for longer than human civilization has existed, repeated millions of times over. The end of the mission is not the end of the object. It keeps going. The story of Voyager 2 is a story about what persists. Atoms forged in a supernova persist for billions of years until something uses them. A spacecraft built in the 1970s persists in interstellar space for decades past its design life. Human curiosity persists through budget cycles and shifting priorities and the retirements and deaths of the people who first cared about this mission. The cold of interstellar space has had nearly 50 years to extinguish it, and it hasn't, because something at the center of this mission has always burned hotter than the darkness around it.